Welcome back, everybody. So as I told you, we are done with the material, but I have questions to ask you just to finish today, and then you will be able to have an early meal. Here's the first one. What fundamental rules of probabilities did we use and apply to information retrieval? Of course. Bayes rule, the partition rule, the pigeonhole principle, or the addition law of probability? Wow, I love that. Please do the same at the exam. Okay. So yes, indeed, Bayes rule. I repeated it so many times. Okay, so Bayes rule is really magical because it allows you to compute things that otherwise you would have absolutely no idea how to compute by swapping the two sides. Okay. Okay, here's another one. There are 3 boxes in front of you. In one box, box A, there are 2 Toblerone. In box B, there is a Toblerone and a Luxembourgerly. In box C, there are 2 Luxembourgerly. You pick a box at random and you take it home, but you don't open it yet. Just take it home. At home, you pick a candy from that box at random without looking. Just put your hand, pick one. It's a Luxembourgerly. What is the probability that the other candy in your box is also a Luxembourgerly? Is it 1/3, 1/2, 2/3, or 1? I think it's called the Bertrand paradox. Thank you very much. I realized that I was on mute the whole time. So we're saying that the majority answer was 1/2, but actually the correct answer was 2/3. And I'm now showing you one. So these are the three boxes: Toblerone plus Luxembourg-Early, and 2 Luxembourg-Early. As you might have guessed, we need to use the base formula. But in order to use the base formula, we need to work a little bit because we need to figure out what random variables we should use. And that is not as easy as it seems, right? So the random variables in this case, that after a bit of thinking that you can use, is one that I call box, which can be A, B, or C. That's the box that you pick. The other one is candy that can be either T or L, right? Either Luxembourg-Early or Toblerone. That's the Boolean variable, right? So I have these two. So now if you formulate the question, it's what's the probability of having picked box C? Because that's when you have another Luxembourg-Early in there, right? So what's the probability that you picked box C, conditioned on the fact that what you have in your hand is a Luxembourg-Early. Now, if you use the magic of the base formula, this is how you swap it. You basically here have the swap, and then with these two correcting factors, right? Now, very quickly and all at the same time, what's the probability of picking box C? I think I heard it, but 1/3, right? Yes, exactly. There's one chance in 3, right? What's the probability of the candy being a Luxembourg-Early given that it's box C? It's 1, right? It's 100%. It's always a Luxembourg-Early. So this is 1. And the probability that the candy is a Luxembourg-Early is 1/2, right? Half of the candy. It's basically, there are 6 possibilities, right, of picking a box, picking a candy. So 1 chance in 2. So it means that you just plug it in, right? So the prior would be 1/3, right? The probability that it's that box. And now the posterior is obtained when you multiply of that 1/3 times 1 divided by 1/2, and you get 2/3. And in fact, the visual of that is that it's really new information, right? Before you know anything, there's 1 chance in 3 of being there. If now I tell you the information, okay, you have a Luxembourg-Early in your hand, that's one of these 3 cases. Out of these 3 cases, which are equally probable, how many of these corresponds to a case where the other candy, the same box, is the Luxembourg-Early? 2, right? If the Luxembourg-Early you picked is this one or this one, that can happen in 2 cases, then the other one is also 1. And the candy here, that would be the third one where it's not, so it's 2/3. For whom is that clear? Right? It's really this visual. You add new information that it's a Luxembourg-Early, and now visually you can say there's 2/3. In 2/3 of the cases, you are in the case that the box is there. And of course, the intuition for many people would be 1/2, right? Because it could be a Luxembourg-Early or a Toblerone. But the thing is, the fact that one box has 2 of them makes it more likely that you would be in that box, right? Another problem that you have in the exercises, did you already cover it, the Monty Hall problem? You will. So the Monty Hall problem is a TV show, and it's also very counterintuitive, and you'll see it in the exercises. Okay, one last question, and then I let you go. The query is foo bar foo. Somebody type that in your search engine. Which ones of the following documents would be returned on top if you use the model I told you? So the more likely that could have generated foo bar foo. If you build a model for, so here you really need to build a model for every one of these documents. And what is the most likely to have produced this query? Bag of word semantics, so corrected with multinomial coefficients, and no smoothing. Is it bar 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 bar, or bar 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 foo, or bar bar foo bar, or foo bar foo bar, foo 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 bar, no foo foo bar bar, foo foo bar foo, and foo 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 foo? So really remember that the model is generating for these documents. And what we want to generate is the query. But because of the Bayes rule, saying that we want to optimize the likelihood of the documents based on the query, it's the same as computing the probability of the query based on the documents, because the other are constants in the Bayes formula. So we need to find the documents that produce that query with the highest probability. By the way, you can kind of also use your intuition here. If you think of it, the first document, for example, would only, if you don't use smoothing, right? With no smoothing, the first document would just generate bar, 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 right? Because it only has 100% of bar. The second document would generate 3/4 of the time bar and 1/4 of the time foo, right? That's the idea that we select the weights based on the term frequencies. So it's 3/4, 3/4, 1/4. The same goes for the third document. The fourth document is 1/2, 1/2. So this would generate half of the time a foo, half of the time bar. Remember the little cats, right? With 2/3, 1/3. Well, instead of 2/3, 1/3, now you have here different weights depending on the term frequency in the documents. Do you want to see the answer? So first, let's see. Foo bar, foo bar, foo, foo bar, foo. That's tight. But the answer is foo, foo bar, foo. And I have, normally, if I got it right, because that's the sort of thing that I can easily make mistakes with. Oh, wow, the first worked here. Okay. So here are all the documents. Remember that we build the model and the weights for each document. So every document gives me different weights. Here it's 100% bar. Here it's 3/4 of bar. Here it's 3/4. Here it's 1/2, 1/2. Here it's 1/2. Here it's 3/4 of foo. And here it's 100% of foo. Again, this is a different model every time. So we need every time to multiply this. How do I multiply this? Well, foo, it's whatever is the weight of foo squared, because foo is generated twice, right? So it's squared and multiplied once with bar. Now, why is the rest just a constant factor? Because the rest, so it's the p-stops that we can get rid of, because the p-stops is based on the length of 3 anyway. That's a constant. But do you see that we can also throw away the multinomial factor? Because the multinomial factor would basically give you the permutation of this, which is a factor of 3, right? There are 3 possible orderings here. Who sees that it's a factor of 3? Right? It can be foo bar foo, or bar foo foo, or foo foo bar, right? But 3 is a constant. It's always going to be 3. So this is why I don't need to care about the ordering. And now if you multiply, this is always this squared times this. So this squared times this, 3/64. 3/64, 2 squared times 2, 8. 2 squared times 2, 8. 3 squared times 1, 9. Now you see it barely wins. It barely wins, because again, here you would have 1/2, 1/2, 1/2, and here you would have 3/4, 1/4, 1/4. So it was very tight. So those who said this one here were very close, but this one actually wins. Who sees it? Right? It's basically just 9 compared to 8. Okay. So how do I stop the sharing? I have no idea how to actually stop. I know how to change the sharing, but I don't know how to stop the sharing. Does anybody know how you do that? Maybe here somewhere. Okay, now I just continue talking like this. So that's it for today. We'll let you go. You can have an early lunch. We are done with the material. Next week we are going to have fun. So there will be for the mystery challenge. Marco will give the prize. We'll also recap. I'll go through all the material of the lecture. And we'll have a quiz. You probably saw it already when you saw my screen, that there's many questions that I prepared. We'll go the Eisgagger 100, right? 1 against 100. You all stand up. And as soon as you get a question wrong, you sit down. You can still answer questions, but the last one who stands up wins. if we manage to convince a few TAs to join, you will compete against the TA team, and we'll see if a TA survives longer than you, right? There is a track record of the students winning, but sometimes the TAs actually manage. So I hope you enjoyed it. Thank you very much. And I'll see you next week for the final lecture. Please come as numerous as possible. If you're on Zoom, then consider coming in presence for the lecture, because then if you win, then it's easier to give you the prize. And thank you very much for being such a great audience. And I'll see you next week. Thank you.